Many automated systems take data and apply some kind of reasoning, called an algorithm, to help make a decision. The more advanced ones can even plan and execute a sequence of actions to reach a specific goal. But the most sophisticated systems evaluate counterfactuals. Judea Pearl and Dana McKenzie called this the ladder of causation in the Book of Why. Seeing is the first rung, doing is the second rung, imagining is the third rung. The type of questions the system can address become increasingly complex as we climb this ladder. At the first rung, association, which is unfortunately about as far as traditional statistics can take us, we can ask, how are the variables related? What if I see X? What then? At the second rung, intervention, there is prediction about the world as it exists and feedback from actions taken in the world, with the possibility of the difference between the predictions and the outcomes driving a learning process. So doing enables learning. And here the questions become active. What if I do X? Does the action I take have the result I expect? At the third rung, counterfactuals, there is a prediction about the world as it might be or might have been. What could I do? What could I have done? So these second and third level systems don't just ask what is the answer. They ask what can we expect when we do or imagine doing things. This is the essence of having a causal world model. The theory behind these systems is presented in the book Active Inference by Thomas Parr, Giovanni Pizzulo, and Carl Friston. A learning system operating in the context of a world model can reason about hypothetical situations and potentially use that information to map out a sequence of actions which is optimal within the limits of the system's current knowledge. That means truth is subjective from the system's perspective, but empirically verified. Feedback from the actions taken can drive learning, expanding the knowledge available to the system, recursively improving future predictions and driving more optimal actions. Alternatively, the book Everything is Predictable by Tom Shivers presents the historical development of Bayesian logic. Shivers makes a number of very well-phrased observations. First, the great insight of probability theory is that we should look at the possible outcomes from a given situation, not what has gone before. The probability of an event is the number of ways we know of that that event can occur, divided by the total number of things we know of that could occur. Probability thus gives a quantitative measure of the things we don't know for certain. It may require a subtle shift in mindset, but think of certainty as a continuous rather than a discrete binary value. 1 can represent complete certainty, and 0 can represent complete impossibility, but the points in between can reflect levels of confidence and skepticism, with 0.5 representing an equal possibility of true or false, a state of complete uncertainty. The key insight of the Bayesian method is that you must add any new information that you get to the information you already have to make each subsequent prediction. Intuitively think of learning by trial and error. When we learn from the errors, we don't make them again on the next trial. Sampling or statistical probability is different from inferential probability. What can we predict about a sample, given that what we know or think we know about the whole, this is hypothesis testing? We don't really want to do that. With inferential probability, we're really asking what can we conclude about the whole given a sample or samples we've taken. Bayes showed how starting with an estimate of what is most likely to be true to your best knowledge, your model, you can make inferences and draw conclusions about what is likely to be true in the world. Consider, as a practical example, the doctor who looks at a patient's data, particularly their symptoms, and has to reason to the most likely conclusion, a diagnosis. Diagnosis guides a decision about treatment, and treatment may or may not result in a cure. Since the world is messy and often ambiguous, data is never perfect. Systems must deal with uncertainty, changing circumstances, and incomplete knowledge. This is where genius agents can help. They're designed for decision-making under uncertainty. The following comes directly from the Genius documentation. Genius agents tackle ambiguity through probabilistic modeling and Bayesian inference. This is very different from the approach of large language models, which are built on a foundation of neural networks. Genius agents use a probabilistic graphical model to represent the world, specifically a directed acyclic graph, which links the model variables, frequently from cause or prerequisite to effect. We'll focus on two related types of graph. The first, discrete Bayesian networks, are a great starting point for introducing the core logic and themes behind how these agents reason and make predictions. Here in the sprinkler example model, the cloudy variable has arrows to both rain and sprinkler, while the wet grass variable is the end point of the arrows coming from rain and sprinkler. The arrows make the graph directed, and the fact that there are no loops makes the graph acyclic. The next step is to add probabilities to each variable. Cloudy is shown as having a 50-50 split. Then rain on the left is shown as having an 80-20 split when it is cloudy, but a 20-80 split when it is not. Sprinkler on the right is shown as off 9 times out of 10 when it is cloudy, but split 50-50 when it is not. Finally, wet grass is shown with 8 different probabilities, depending on the 4 states possible for the 2 variables sprinkler and rain. For example, in the first column, when the sprinkler is on and there is no rain, there is a 0.9 chance of wet grass. The notation for expressing these conditional probabilities uses a vertical bar to denote given. When a probability has multiple dependencies, they are listed separated by commas. A factor graph replaces the arrows connecting variables with these probability tables, which are then referred to as factors. This sets up the system to make 2 types of inference. First, a forward inference, also called conditioning, where, for example, an observation of either the rain falling or the sprinkler running in green allows for the inference of wet grass in red. Or the inference can go in reverse, so observations of wet grass with a sprinkler running in green can be used to infer the chance of it being cloudy in red. The next lesson will cover how the variables, states, and factors come together in Genius.